find out? Okay. So on your graph there, that thing went down from 10 meters to 8 meters. It did that in 4 seconds. And you can see because that line curves that it doesn't have one velocity the whole time. It starts off slow and then it goes fast, but its average velocity, since it went down 2 meters in 4 seconds, 2 meters divided by 4 seconds makes 1/2 meters per second. But because it's going in the down direction, it's really negative 1/2 meters per second. All right, so I'm going to do a circular trick here. Camera people, thanks for your patience because I know I had to point it in a weird, point the camera in a weird way. Let's see, y'all can see me over here, right? So I had just demonstrated with the door that if I push here, it's real easy for me to push, for me to make the door move, because there's no mass that's outside here. I'm pushing the farthest away, like all the mass is inside the point where I'm pushing. And that's what makes it real easy. If I push way over here, most of the mass of the door is outside the point where I'm pushing, farther away from the point. The point where I'm pushing is closer to the axis of rotation, and all the mass is now farther away, and that's what makes it really difficult. So keep that in mind as I do my next trick here. Okay. All right, I'm on a spinny thing, people who can't see back there. Are y'all gonna watch me? Because I feel like an idiot for nothing. Okay, here we go. So what I'm gonna do, I'm gonna lift my hands out to my sides. So they're out to my sides, people on the camera. And whenever my hands aren't down here, they'll be out to my sides, like a T. Okay, ready? See if you can relate what happened with the door to what's happening with me out here. So I'm going to start with my hands out. Okay. Okay. Yeah. What happened when I brought my hands in? Yeah.
Faster?
What happened now?
Slower?
Yeah, I'm slower. What about now? Faster? Wow. Why do you think that happened? Oh.
You lessen the mass outside.
It's all about the same thing as the door.
Rotation point.
Yeah.
Yeah.
All the mass close, so the force didn't have to work as hard.
Yeah, it takes more energy to rotate me if my arms are way out here, because there's my rotation, my axis of rotation is here. My arms, when I move my mass outside my axis, farther outside my axis of rotation, I'm gonna spin slower because it takes more energy to rotate me. But then when I bring my hands in, it doesn't, all my mass is to the inside, and it's easier to spin me. Just like when those ice skaters, you know, when you see them do their jumps and whatever, their jumps with the spins, they go, they cross their hands like this and make their mass as close to the center of their body as possible, right? And then they spin real fast. Have you seen that?
Yeah.
You're like, we don't watch those kind of Olympics, Mr. Franklin. Well, that's what they do. It's physics. So I'm going to do this with weights now. So this is the same thing like if you ever been on a merry-go-round. I know, you know, they only have those at the old playgrounds, but it's the same thing. If you start on the outside of the merry-go-round, that's like when I have my arms out, because all the mass of that circular merry-go-round is on the outside of it. If you start, like right when you get onto it from the outside, if it's spinning, let's see. Okay, I got these 2-pound masses in my hands now, so that'll work. Okay, I spun myself a little faster. I pushed on the thing. Ready? Zoom. Oh, God. Oh, God. Okay. And zoom. So if you go to the center of that merry-go-round, you'll spin a lot faster, and then you can slow yourself down if you go to the outside of it. Zoom. Okay. Oh, yeah. I'm just going to stay here for a minute. It's a little busy. Okay. Oh. I'm almost ready. Okay, I'm ready. I'm ready. So, that's one circular thing. Here's another circular thing. Look at these. Are you looking? Look. I have a plastic one, and a wood one. The plastic one is actually a little bit heavier than the wood one. We are going to have them race to see how they do on these ramps. Yeah, that's what we're doing with the ramps. I know you were wondering about the ramps. It's like, what is that, Mr. Finger? Okay. Okay. Are you ready? You looking? Here they go. Oh, exactly the same, right? They stayed exactly the same. I'll try them in a different order. Let's see. So maybe y'all can see better if they right here. Let's see. Let's see what they do. Okay, ready? Did I mess that up? This one won. This time.
According to the law of,
Let's see. Well, I'm gonna try one more time. Because I haven't seen this one win before. We have to see if that's for real or not. They were closer that time. I wonder if this, because the thing with these are, if they have the same mass distribution, they ought to have the same, they ought to tie at the bottom. I think I'm hearing the fan. Something was ringing. So, let's try, something is ringing. Yeah, I think I'm talking and it's making it vibrate. Okay, so, let's try, I'm gonna use this plastic one because it's, the wood one gets dented more easily. I don't want it to get messed up here at the bottom. Let's try these. Now think about what happened with the door and what happened with when I was spinning around right there. Which one of these do you think will win based on their mass distribution? How far the mass is from the axis of rotation here. And will that make it more difficult or less difficult for it to roll down? What do you say?
plastic.
You think a plastic will win?
Mm-hmm.
Anybody else have a different philosophy here? We'll try it out. I'll put the plastic one back so we can see. Alright. Alright, ready? Yeah, the plastic one did win. Look at that. Try it the opposite way. Make sure that that's not, make sure that that's for real. Ready? That was a good one. The plastic one is definitely winning. Okay. And that's right. See, what's happening with this is gravity pulls on this whole thing. So it pulls, you know, it doesn't know what it's shaped like. It pulls on the whole thing. So it's pulling from right here, from its center of mass. And pulling from right there, because its mass is so far away from the axis of rotation, that makes it really difficult for gravity to pull on it. So it accelerates more slowly because the mass is so far from its axis of rotation. It takes more energy for gravity to get it going. So that's to pull way on the outside. This one, its mass is more spread out throughout the thing. So gravity's pulling right here, but since not all of its mass is way out here, more of its mass is toward the middle, it's easier for gravity to get it going, and that's why. Let's try these two. So this is a smaller ring. This ring is a little bit thicker. If y'all can see if I can line them up so y'all can see it. See, can you see it? The ring that's closer to me is just a little thicker than the other ring. Can you see it? Camera people, which way is the camera pointing? Well, that's difficult to do. Yeah, it's just a little, the ring on the right, on this ring, is a little thicker than the other ring. Anyway, let's see what they do. So the ring that won that time was the heavier ring. I'm going to put the heavier ring on this side now and see if I didn't mess that up with my hand, because I hadn't seen that before. Ready? that's what's supposed to happen. They end up doing the same thing. And it's not about how much mass they have. It's not about how big they are even. If you took this ring and made it 100 times the size of this ring, they would still roll at the same rate. It's just about the mass distribution. It's about how far, what percentage of its mass is far away. Are y'all paying attention? Stop it. You're not paying attention. Stop what you're doing and pay attention. If the same percentage of its mass is far away from its center, the same percentage of its radius away from the center of the thing, then it'll be that much faster. Yep. And that's all I have to say about that. Please try this out. It's a circular thing.